Atomic mass. So we talked about isotopes and what they are. Let's look at chlorine. Chlorine has two naturally occurring isotopes, chlorine-35 and chlorine-37. Now, the mass of a chlorine-35 atom is 34.97 atomic mass units, and the mass of a chlorine-37 atom is 36.97 atomic mass units. The atomic mass will be very similar to the mass number. It's not going to be exactly the same, though. And I cannot give you a quick explanation for why that is. It's going to be really close, though. And we know from experiment that 75.77% of the chlorine is chlorine-35, 24.23% is chlorine-37. Well, when we deal with chlorine gas, or chlorine in any form, we are almost always dealing with this mixture of isotopes. And so what we want to know is the average mass of chlorine atoms, not the mass of these two different kinds. We want the average, because we're going to always be dealing in gazillions of atoms, and so we don't care about the individual ones. So we calculate the average atomic mass based on the percentages. So it's a weighted average, because nobody wants to add up these masses for 5 billion atoms or something. So what we do is we take the percent abundance and convert it to decimal form. That just means we're dividing it by 100. So 75.77%, bless you, is 75.77 per 100. So that's going to be 0.7577. We take the decimal and multiply it by the mass of that isotope. Here's the other isotope, 0.2423 times its mass, and then we take those numbers and we add them up, and that gives us the average mass. We can't do a simple average, just add them together and divide by 2, because it's not 50-50 of each. There's more of the chlorine-35 than there is of the chlorine-37, so the average mass is going to be closer to 35 than to 37. So this is a more math way of describing this. The atomic mass is the sum of, for n different isotopes, the fraction of isotope n times the mass of isotope n. And you add each of those together, however many you have. Let's do an example. Magnesium has 3 naturally occurring isotopes with masses of 23.99 AMUs, 24.99 AMUs, and 25.98 AMUs. And natural abundances of 78.99%, 10.00%, and 11.01%, respectively. Calculate the atomic mass of magnesium. What I'm going to do is I'm going to take this percentage and divide by 100 to make it into the decimal equivalent, so 0.7899, and I'm going to multiply that by the mass of that isotope. I'm going to do that for each of the 3 isotopes and add them together. So 0.7899 times the first one, because respectively tells us that they are listed in the same order. And then I'm going to add 0.1000 times the mass of the second one. And I want to include my units here. And I think I'm going to run out of room, so I'll just go on to this next line. 0.1101 times the mass of its isotope.
So it's always the mass of the isotope multiplied by the natural abundance percentage?
Yes. It's the mass of each isotope multiplied by its relative abundance in the decimal form, not the percentage. If you did it with percents, then you'd have to divide by 100 at the end. So then on my calculator, I can just do this in one calculation, 0.7899 times 23.99 plus 0.1 times 24.99 plus 0.1101 times 25.98. And my calculator gives me 24.309099 atomic mass units. Did anybody get that number? Thank you. Okay, then we have to think about significant figures. Like with temperature, there's some funny things that can happen occasionally. So you can do the rigorous thing with the sig figs, or you can look at decimal places and numbers of significant figures. Here, my percent abundances have 4 significant figures. That means that my answer can't have more than 4 significant figures. And I'm going to end up with, I shouldn't end up with more decimal places than I had in my masses. So based on that, I'm going to round this here and say it's 24.31 atomic mass units.
And did you base the sig figs off of the multiplication aspect of the problem or the addition?
Did I base it off of multiplication or the addition? What I really did is I looked at the 2 different types of numbers I had. I have percentages and I have masses. And in this case, they both have 4 significant figures. Some cases, though, you'll have the mass with 6 or 7 significant figures, and the percentage will only be 3 or 4. Then the percentage is going to limit the number of significant figures in your answer. But it could happen the other way around as well. I'm not going to try to trick you on sig figs with these. Any questions? A quick check to see if you really screwed up. This number has to be between the highest and lowest value. An average can't be higher or lower than the highest or lowest value. So 24.31, here's my smallest one, 23.99. This is larger than that, and it's smaller than the largest one. If it's outside, then you screwed up something somewhere. How do we figure out what the mass of these things are? How do we find the percent abundances? Well, we use a technique called mass spectrometry. And I want to tell you about this, but I'm not planning to test you on it. This is a technique that separates particles according to their mass. And it'll give us information like this. We can separate the chlorine-35 and the chlorine-37 and get, based on the intensity of the signal, we can get information on the relative amounts of each. So this is how it works. Your sample is vaporized, converted to a gas, and sent down this tube where an electron beam ionizes the samples. It's hard to get particles to move if they don't have a charge on them. If they have a charge on them, you can do all kinds of stuff to them. So we want them to be charged. And then here we have an electric field that's going to accelerate them, get them moving quickly. And then we send them through this magnetic field. The magnetic field is going to separate the particles based on the ratio of their mass to their charge. And the heavier particles will be deflected less, and the lighter particles will be deflected more. And so based on the intensity of the signal that you get at this detector and the position of the signal, you can get the relative abundance of these different substances. And we actually have a mass spectrometer on the other side of that wall, which is really cool.